Hello, my name is Minh, and today I'll be presenting the research I conducted in collaboration with Samira and Lawrence titled User-Defined Co-Speech Gesture Design with Swarm Robots. In interpersonal communication, humans use various nonverbal cues such as eye gaze, facial expressions, body posture, and gestures to convey information and complement verbal discourse. Among these nonverbal behaviors, gestures that synchronize with speech, known as co-speech gestures, have garnered significant research attention. Psychology and neuroscience studies suggest that in human communication, co-speech gestures improve conversational dynamics and reduce cognitive load. When implemented in robots, these gestures enhance their perceived liveliness, likability, and social abilities. Despite the benefits of co-speech gestures in robots, several challenges hinder their widespread adoption. Many humanoid robots are costly and large, making them impractical for everyday use, while smaller robots lack the sophisticated actuators needed for realistic human-like gestures. Additionally, humanoid robots can trigger the uncanny valley effect, making them feel unsettling to users, with studies suggesting that non-human designs can sometimes feel more natural. Nevertheless, literature research has explored co-speech gestures in non-humanoid robots, with most works focusing on specialized robotic tasks rather than general conversational use. To address this gap, our work explores the novel use of swarm robots for generating co-speech gestures. Prior research has shown that tabletop swarm robots can serve as scalable user interfaces, effectively conveying information and expressing emotions. It is also suggested that humans can quickly interpret the intent of the robotic swarm's movement, making them a promising medium for co-speech gestures. Building on animation principles, which suggest that people naturally interpret simple geometric movements as social and intentional, we hypothesized that swarm robots can use their movement and formations to convey meaningful co-speech gestures. However, the specific gestures that best align with different speech types remain unclear. While expert animators could design these gestures, their choices may not reflect user preferences. Therefore, three key questions guide the current research. First, what swarm-ray gestures do non-expert users generate for different speech instances? Second, do these swarm-based gestures enhance human-robot interaction in general conversation? And third, how can these gestures inform the software and hardware design of future swarm robots? To answer these questions, we conducted a two-step investigation, a user elicitation study where participants create swarm-based gestures for given speech instances, followed by a comparative evaluation study to validate the gesture's conversational effectiveness. In the elicitation study, we presented 20 participants with audio recordings of single words, simulating a swarm robot system speech, then asked them to design corresponding co-speech gestures using robot movements and formations. The setup included 10 Toyo robots on a 40 by 40 centimeter square tracking mat, with speech audio projected from a laptop and word definitions displayed on a monitor. Using an overhead camera, we recorded participants' physical manipulations and verbal explanations of the gestures. 40 relevant words were selected across four semantic categories: action, object, characteristic, and relation, from the corpus of contemporary American English. Each participant completed 20 trials, each corresponding to a different word, with word choice and order randomized for balance. In each 2-minute trial, participants brainstormed the gesture, then recorded robot speed, quantity, start and end positions, and perceived speech gesture alignment on a provided worksheet. A post-study survey gathered insights on task strategies, challenges, and design suggestions. Building on prior research of user-defined designs, we analyzed participants' generated gestures using a systematic taxonomy. The function of each gesture was categorized as metaphoric, iconic, abstract, didactic, or symbolic. Group characteristics included the number of robot groups used, their collective formations, such as lines or symbols, and movements, such as stationary or transform. Individual characteristics considered the number of robots involved and their movements, both external, such as straight or curve, and internal, such as spinning or jittering. To measure participants' consensus, we calculated an agreement score for each reference word. Finally, we conducted statistical tests to examine differences in speed preferences, robot quantity, and perceived gesture meaning alignment across semantic types. This figure shows the taxonomy distribution of participants' generated swarm-based co-speech gestures. Iconic and metaphoric gestures were the most common, with iconic gestures most prevalent for nouns and metaphoric gestures most frequent for adjectives. Robot group formations could balance between singular robots, lines, and basic shapes, with most group movements being simple, such as transform or back and forth. Individual robot movements were predominantly straight or curved, with internal movements like jittering and spinning being rare. This figure shows agreement scores for co-speech gestures across all reference words. The average scores by semantic type are 0.26 for adjectives, 0.43 for nouns, 0.37 for prepositions, and 0.18 for verbs. These scores will later guide the selection of our gesture set. Statistical tests reveal significant differences in preferred robot speed across semantic types, with verbs and prepositions eliciting faster movements than nouns and adjectives. This likely stems from their reliance on dynamic gestures. Nouns, in contrast, prompted the use of more robots, likely due to their association with iconic gestures requiring larger formations. However, no significant differences were found in speech gesture matching or the number of robot groups used. Overall, participants favored medium to slow speeds, using an average of 8 robots and 2.4 groups per gesture. The post-study survey showed that participants relied on simple visual representations or familiar human gesticulation to create swarm-based gestures, such as using a moving arrow to represent two words. However, 11 participants found it challenging to brainstorm gestures for abstract words, while 7 noted that the limited number of robots restricted their ability to create complex shapes. Additionally, 9 participants suggested incorporating colors, such as red for medical, and 7 would prefer circular robots than the square toys. Using to analyze agreement scores and participants' preference for simple, familiar visual representations, we developed a foundational co-speech gesture set. The full set can be found in our paper. To validate the co-speech gesture set from the elicitation study, we conducted a comparative evaluation study within a voice assistant, VA for short context. As prior works have shown that physical embodiment of personal assistants enhances perception of their social abilities, while incorporating gestures improves perception of their movements, we compared VAs equipped with swarm-based coach speech gestures to those using simple animated movements, with the following hypothesis. H1. VAs with swarm-based gesture will be perceived as more animated, likable, and intelligent than animated VAs. H2. The gestures of swarm-based VAs will be viewed as more fluid, semantically aligned, and temporally synchronized than the movements of animated VA. We presented 30 participants with 17 video pairs, each representing a word from the co-speech gesture set. In each pair, 2 VAs answered the same question with identical answers but different movements. For example, for the question, how do I get to the supermarket? Both VA would respond, go around the building, and their differing movements start during the response. Participants rated the VAs on 6 characteristics: animacy, likability, perceived intelligence, fluidity, semanticity, and synchronization, using a 7-point Likert scale. The order of VA presentation in the video pairs were readily balanced, and the data was processed, such as a score of -3 indicated animated VA is significantly better than swarm-based VA, 0 indicated both VAs are equal, and 3 indicated swarm-based VA is significantly better than animated VA. Statistical analysis found that the swarm-based VA was perceived to be more animated, likable, and intelligent than the animated VA, supporting H1. The gestures of the swarm-based VA were also viewed as more fluid, semantically aligned, and synchronized, supporting H2. These findings suggest that swarm robots can enhance conversational systems by providing expressive co-speech gestures. Their potential extends from multimodal voice assistants to interactive storytelling and education. By integrating natural language processing, swarm robots could generate real-time gestures that enriches narrative performances and classroom learning. The results also provide insights for improving swarm robotic hardware and software for co-speech gestures. Participants typically group 2 to 3 robots for synchronized movements, but current platforms lack support for collective coordination. Therefore, future swarm robotic software should support group-based formations and movements, while hardware should enable a wide range of speeds, at least 10 robots, and finer internal movements like jittering or spinning for better gesture expressiveness. One limitation of the elicitation study is the use of single-word speech units, and future research could examine gestures for long phrases and complex sentences. Additionally, as the evaluation compared swarm-based VAs to animated VAs, future work could extend the comparison to humanoid gestures. In summary, this study highlights swarm robots' potential for expressive nonverbal communication beyond humanoid designs. Thank you for listening to my talk.